Okay. Hi, everybody. My name's Pete Fine. I want to welcome you to the Pittsburgh Python meetup. If you found this group through the Code and Supply event, there's a separate meetup group just for the Python-focused stuff here. And we're just kind of trying some new things in terms of how to do publicity. Along those lines, if you haven't already, please consider joining Code and Supply, just as a way of thanking them for the support, making the space available. There's lots of great events here, and it's our dollars that keep the space running. Tonight, we're going to have Jesse Legg talking about async I/O and robots. If you're into robots, August 4th, which I believe is a Saturday, Code and Supply is having like a community-wide Too Many Robots event where you're encouraged to bring out your robotic best and see what everybody else is doing. What else is going on? Upcoming Python events. Next month, we have Bartholomew Elliott talking about linting, static type checking, type hinting, and other tools you can use to make your source code higher quality, more reliable, and kind of some automated tools you can use to do that. In September, we're going to do a roundtable, a bit of a different format than just one person up here talking, on Python distributing and packaging. So everything from how do you write a setup.py and put your code on PyPy to packaging Python code for deploying with Docker or just to get checkout or whatever it kind of people is, and just sort of trying to facilitate a discussion about the different ways and challenges that people have dealing with this issue. Personally, I'm hoping somebody can explain Conda to me, because I have no idea. I just come from totally the other, like more the systems end of thing, and so all these, we're hopefully somebody from the data science side can clue me in. Yeah, and then of course we're always looking for speakers. You have it in you. You really do. And it's also kind of a great way to get more experience doing public speaking. And I also find, having done this, that doing talks like this are a really good way to sort of, you have ideas for a project to work them through, that being forced to kind of communicate what you're working on to a public audience can help you refine the work itself. So if you're interested, we're looking for people for October, November. December we'll probably do something a bit more low-key, or maybe just go get drinks or whatever. Yeah, and so without further ado, we do a monthly thing here. We call it Module of the Month, which is a review of a helpful library or package in Python. It's based on this super helpful site called Python Module of the Week. This is actually a book now, where the author goes through the standard library and picks out some of the best parts and tries to show it by practical example, as opposed to more kind of an API documentation. We're coming back to something I use occasionally and find helpful in the collections module. All sorts of good stuff in here. This library is called ChainMap, and like it says on the cover, is used for searching multiple dictionaries. And so can people see this? Should we make this bigger? Probably bigger. I see people straining. Okay.
It's out of focus slightly.
That I can't do anything of here. Try.
Maybe it's
Any better?
oh, yeah,
Okay.
get a few drapes closed.
Sure. Can somebody pull some of these?
Crystal.
Yeah, it looks great. So the idea behind a chain map is it's the dictionary API, but backed by a sequence of dictionaries. So if you have, say, two different dictionaries, A and B, when you go to, you can chain map them together, and it will look up the keys in order. Kind of see that here. So far, this is a really simple but quite helpful module. Those mappings are kept in this maps attribute. Find that down here, and that's mutable, so that if you have say a sequence of three mappings, you can reverse them, search them in the opposite order, stuff like that. there's no, beyond that, there's like no direct access to those underlying dictionaries. And so the behavior for when you add a new item or update an item is kind of a little potentially funky. And Python chooses, in that case, that if you insert a new item or update an existing item, that applies to that first dictionary in the sequence. All right. There's also this handy, let me find this, new child method, which basically like creates another chain map with like a new empty dictionary on the front. So it's like kind of creating a new context. And so that's where these things are often used, is when you have like one of stack nested context. So let me see, this had some really nice examples over in the standard lib docs. Hold it here. So for example, this is right. If you and this is, you can think of this as a way of implementing nested scopes. So right. So when you look up a variable name in Python, it looks in your local scope, and then your module scope and your global scope, and that's kind of a similar set of namespaces that you could implement with a chain map. So this can be useful writing interpreters. If you're doing template languages, like Django's template language does something similar under the hood, where you have variables defined in kind of multiple contexts that are layered on top of each other. The other thing that this is cool for is merging settings from multiple locations. And so the standard library docs have an example where you pull out settings from environment variables, but can override them with config flags, which you can see here, right? It makes it a really an easy way to implement this quite quickly. You could stick default hard-coded defaults or a file in there, and it kind of makes it sort of simple. Similar to class inheritance a little bit, if you think about it, is sort of looking up to resolve a name. Name a method, you look up an inheritance chain. And so I've used this writing interpreters, writing compilers, like to implement like local or nested scope. Anybody else think of any good examples to do with this thing? Anybody used this before? Okay. Occasionally helpful, and not something I use every day or even every month, but really a nice example of the batteries included philosophy that Python has, that this is just this helpful utility that somebody's written at least once, every 10 years, and so let's write a high-speed, like high-quality version that we can all have. So, chain map, there you go. And without any more nonsense, I'd like to give you Jesse, who's going to talk to us about async and robotics. Thanks a lot.
Totally.
You're good.
Cool. All right. So this has been a long week for me, and this is like one of the most complicated topics in Python. So we'll see how this goes. I also, about halfway through like putting this together, realized I kind of hate async IO. So if I'm a little bit like antagonistic, that's why. I've been doing twisted async programming for about 2 years now, year and a half, and I hated twisted too when I first started using it, and now so async IO has always been kind of like a hobby thing on the side, and maybe getting my code base into async IO eventually. This was like me kind of strapping down and like really like trying to organize my thoughts around async IO, and I really appreciate some of the stuff that twisted does relative to the two. And if you look on the internet, there's actually a lot of criticism sort of to a similar effect. So kind of an interesting thing. We can get into that a little bit. I divided this up into 4 parts. First part is just like async programming 101, so not specific to Python, but just kind of in general. The goal there, I'm going to try to, like, if you've never done this before, I'm going to try to like go through the model, the paradigm of how async programming works. If you've done Node.js or JavaScript, you probably already know. Second part is a kind of a deeper dive into async IO as a module, the standard library module that we have now in Python 3.4 and later for async programming. And then parts 3 and 4 are more about frameworks like Twisted and comparisons to those, what other async things are going on. And then use cases, robotics and IoT, the web server use case, which is kind of the common one. So that's how we'll structure it. So here's my attempt at explaining what async programming in general is. So determinism versus non-determinism, right? Normally when you're programming sort of deterministically. Step 1, step 2, step 3. It's like a recipe. Async programming is totally different. It's non-deterministic. So what does that mean? So normally, step 1, step 2, step 3, right? Go to the store, go to my friend's house, go to a show with them, right? Straightforward. It's like a recipe. Non-determinism, it's my analogy. You go to the store and then you text your friend and you're like, hey, do you want to go to the concert? What happens next? Like, what do you do next? It's not clear, right? You've actually created multiple universes. It's kind of like quantum mechanics. So he could get back to you right away. He could not get back to you at all. He could be like not interested in going, get backing, and you have to do a negotiation. So you kind of have these different scenarios, right? He gets back to you right away, you just go. That's great. That's sort of deterministic, but not really, because you don't know how long it's going to take for him to get back to you. If he doesn't get back to you, then it's not clear what you do, right? Like, what do? You just wait, go by yourself, call him, go to his house, whatever. So non-deterministic. It was my attempt at an analogy. So synchronous programming is deterministic, generally. Asynchronous programming isn't. So what does that mean, really? If I'm trying to get a URL from a web server and I'm using the requests module, right? Requests will sit here forever, waiting for that server to respond with a response. It won't actually be forever. It has a timeout value. So if it hits that timeout and it doesn't get it back, it'll throw an exception. But essentially, it'll just like stop everything. Your program will stop running, and you'll wait for the server to get back to you. What if the server's down? What if the server's really slow? It's overloaded. All these different situations can come up. It kind of like, it's not clear what will happen. So what you would like maybe is to do something asynchronously, meaning go do this, like go talk to the server, send the request out. When it gets back, let me know. But like, what does that even, how would you do that, right? Like if this line executes instantaneously and then your program continues, how does that even work, right? So there's something that has to be there. That's what asyncio and similar libraries provide, is an event loop and some other stuff so that you can do things like that. Node.js is actually sort of the canonical example at this point of this type of programming. So in general, there's a sort of general pattern to how you would do this. Get an event loop, schedule a task with that event loop, and then handle the response in some way. Tell the event loop, when you're done, here's how you get back to me. In asyncio and Python, this is an example of kind of the basics of that. This example is old, actually. AIO HTTP right here changed their interface, so it actually doesn't work like this anymore. But this was better for my example, so I'm using like the old version. You'll notice, first of all, we're not using requests. So we couldn't make the GET request using requests because requests is a blocking library. It's synchronous. It's not going to do asynchronous response. It just doesn't. It probably never will. So this AIO HTTP library is one of several different things you can use to make asynchronous HTTP client servers. So that's one thing. I've bolded kind of the weird stuff. This asyncio decorator, coroutine decorator, we'll explain coroutines more in a minute, but that's necessary to kind of make this all work. You also have this yield from thing. Yield from is a little weird. This is why I used the old version of AIO HTTP, because I wanted to demonstrate this. This is actually not specific to async programming in Python. This could be used for different things. It's sub-generator delegation. So if you write a generator function and you want to sort of like call into that and return a value from it, you can do the yield from and kind of get everything marshaled back and send it back. But for the first versions of async IO in Python, this is how you had to do it. So that's that. And then this is the construction of the event loop. And then we're saying, run this thing that I define, this task. until it finishes. And so we're basically saying we don't care what happens, like we don't want any response really, we just want you to run this. And this is pretty low level. I realized I wanted to kind of keep this broad and sort of like an overview of things. I do get pretty deep into some of the async IO stuff. It's a little maybe too low level, so I apologize for that. But you would generally do more sophisticated things than this. But this is like illustrates the example, I hope. So brace yourselves, it's going to get worse. This is concurrency, right? Like this is what asynchronous programming is. Sort of, not really. It's concurrent in the sense that we've dispatched a bunch of stuff, right? Like we're talking to servers and we're waiting for them to come back, for example. Those can all kind of be happening concurrently, but our program is only running one thing at a time. So we have this event loop and it's scheduling these tasks. Each task will just run in a serialized fashion. So while technically that's kind of concurrent because you're waiting on things to come back from the IO stream, it's never going to actually execute things like, like in a thread, like threads or something where it's like sort of very close to concurrent. It's serialized. What that means is, and it's also single threaded, just like Node. If one of these tasks has a problem, and it's, say, using the requests library instead of the AIO HTTP library, it's going to block your entire program, including everything else that's waiting on a response. It's just going to sit there. That's a problem because now you're just stuck. Everything's stopped. Everything's grind to a halt. Very, very difficult to debug that type of thing. One of the bigger kind of issues with asynchronous programming as a paradigm. So pros, it's nice. You can kind of manage state fairly easily because you don't have to worry about things kind of overlapping each other and blowing things away. You still need locks and other things for sort of certain kinds of interactions, but in general, it's easier than like threads or multiprocessing. It's also really high performance, mostly for network IO apps. Cons, it's complicated. It's really complicated. You can get this single thread blocked thing if you screw up or write a bug. Things can go haywire pretty easily. And it's really not a good idea or not recommended to mix synchronous code and asynchronous code, mainly for the second bullet point. Because if you use the requests library, you block the thread, everything sort of stops. So in general, that's hard. It's also hard the other way. It's not hard, but you just have to be careful what you're doing, especially when you're doing I/O. For example, in Twisted, there's people will plug in like third-party logging modules that they won't realize are blocking, and they're logging stuff out, and every time they log, it's blocking, and like that throws the whole system out of whack. All right, so the module itself landed in 3.4. It's been there for a while. It was kind of a mess initially. Like I said, I kind of grew to hate it as I was putting this presentation together. It's kind of still a mess. It's much better with the async and await native coroutine syntax, which we'll talk about, but it's still kind of rough. So it has 3 parts: a pluggable event loop. So it's an abstract interface for defining event loops. So these different frameworks like Tornado and Twisted and other async frameworks can use a common event loop definition, and then that way there's more interoperability. That was the idea. I know Tornado is adopted to this really well. Twisted is, you can use the async IO in the Twisted reactor, but I'm not sold on the interoperability argument so far, but it's, that's kind of the thrust of the reason for doing this. It's also nice because you can do third-party event loops that might be faster, like UV loop. There's some other third-party things. Then your other frameworks could, in theory, use those. The other piece of it, sort of these generic definitions of transports and protocols. So transports are sort of like the movement of bytes, right? Like two-way buffered streams would be a transport, and then you'll run a protocol over top of it, like HTTP or something like that. There's basic support for those things, like basic HTTP client server stuff in async IO itself. Things like AIO HTTP are a little bit, they're sort of like the requests of async IO. So like as with the original Python library, URL lib, and some of these other things that are kind of hard to use, so somebody went and made requests. Same sort of idea here. The built-in stuff, I think, is a little tricky. The third piece is the scheduler. So this is what lets you send stuff to the event loop, have it get scheduled to run. There's a whole set of different things you can do to do this. This top bullet point here is kind of the most the easiest to understand. So call soon. As soon as you can, I'm giving you this function, run it. Call later, wait for some period of time and run it. Call at this specific time, run this thing that I'm giving you. That's a pretty common kind of pattern. Twisted has the same stuff. Most asynchronous programming event loops have that type of thing. So how to use a scheduler? Pretty easy. We just went through it. You get your event loop. There's a get event loop call in asyncio. You get the loop object, and then you can schedule things to run. You also have to start the event loop, which I'll show in another example. Futures. So this is one of the complaints that I have with asyncio, and I think other people do. There's like all these different, there's just a lot in it. It's like all these kind of mishmash of things. So we saw transports and protocols. It's got futures and tasks. Futures are sort of the parent class. Tasks inherit from that. You'll mostly use tasks, but futures are important to understand. It's hard to explain. Futures are basically like promises in JavaScript. I think an example is more helpful. They just sort of represent a place where you're going to put stuff in the future and keep track of whether your thing ran or whether it failed. You can add callbacks to them, stuff like that. So this is sort of an example of working with them. You will almost never write something like this if you're actually using asyncio, but I wanted to kind of illustrate the sort of guts of how this works. So you've got this function that you want to call. You're creating a future. You're scheduling it to run. You tell the event loop to start, so just run forever. At some point, after 30 seconds, probably close to 30 seconds, it will run your function. The function will get a future object, which will put a result into, and then it'll stop the event loop and return control back to the comment line after the run forever. So it'll stop everything. When it gets to this point here, it's just going to sort of freeze. It'll look like it's blocking, but it's not. I mean, I guess it kind of is, but it's running your event loop, so it's doing all this stuff. So when you call stop, this ends, you fall back in here. We can use that future object to get the result of the calculation, print it out, do whatever we want with it. And then closing the event loop is just kind of a cleanup task. So that's futures. You don't usually kind of do things this way. Usually the recommended thing is to use tasks. Tasks are direct subclass to futures. The only other thing they have that futures don't, besides kind of the machinery inside of them, is a cancel method. So you can cancel it after it's created. I've also written this as a coroutine instead of the callback stuff. So the callbacks can't be, those are what you would schedule directly with the scheduler. With tasks, you can write your async function in like an async fashion, define it as a coroutine, create a task around it. So the task knows how to take that and sort of like turn it into the future object that it needs to run in the event loop. So we define that. Creating a task directly like this will schedule it right away. So like you're putting it into the event loop, it's going to run as soon as it's available. It's like a call soon. It's automatically scheduled. You start the event loop, everything runs. Usually you'll do something like this, and this first thing that you schedule here is like your main, and the main will like start the application logic for whatever your application is supposed to do. So you would see this pattern kind of for that. In this case, it doesn't do much. It does one request to a web server and it returns a result. That's it. All right, so native coroutines. In the previous slide, we did this decorator stuff to define a coroutine. In Python 3.5, we now have this nice syntax, which is a lot easier. Basically, just does the same thing, but makes it more clear. Yield from is really confusing since you can also use it for generator stuff. If you have this actual explicit async def, you're saying this is asynchronous. So treat it that way as a, for future developers that are working in your code base. So that's really nice. The await is a little nicer, but it's very similar sort of idea.
So just to be clear, this is just sugar, like syntactic sugar for wrapping something in a coroutine and then yield fromming it?
Essentially.
Is that what we're doing here?
Yeah, essentially. I mean, this is a syntax that was borrowed, stolen from other languages.
Sure.
C# and JavaScript, probably the main ones. But yeah, it's basically, you can write them either way. You can use that decorator, or you could do this if you're at this version. This is probably better because it's more clear. I think the reason they didn't do this initially, or one of the things in the PEP that they talk about, is that there were like things in the code base defined with these names. And so to turn these into keywords was tricky, right? So there's actually a deprecation schedule for, I think these are actually some special kind of token in Python until this thing is deprecated out. But yes, basically syntax. So this is kind of a full example, right? We looked at callbacks earlier with the future thing. We're doing a coroutine with native coroutines. And we're putting it all together. We're creating a task out of that coroutine. We're adding a callback, so we can add this done callback thing. There's other types of callbacks you can add too, but this is when it's done, call this function, and you'll get a future object. The future object will just be essentially this, like the async syntax will take care of turning that in the task. Between the two of them, we'll turn it into a future. When you get it, you can grab the result, print it out, shut down your loop, close everything. That's it. So kind of low level. This is actually more of what you would probably start doing if you were to use asyncio directly. You're not going to use like a framework around it. And like I said earlier, usually you would be creating a task out of like your main thing. Your main thing can create tasks for application logic and other stuff inside itself. And you can do this all kind of inside a function somewhere or inside a coroutine. But so that's sort of the general pattern. So kind of brutal, right? Like, I mean, I don't know. I don't want to be too negative on it, but it's like I've gotten a little frustrated going through this. More stuff that you can do with 3.5. Context managers and asynchronous iteration or for loops. I find this a little magical. It's fine. It's kind of neat. It's neat. Like, I mean, I think it's good overall, but it sort of takes a while to wrap your head around. If you say need something that needs a lock, you can do this async with lock thing or whatever you want to wait for. And it'll just pause the event loop until that comes back and you get the access to the lock, and then it'll fall into your typical kind of context managed with statement. So you can do stuff, and everything inside this block would be guaranteed to happen after you get that lock, or whatever it is. It could be data from a database or some server or whatever. So that's kind of nice. Likewise, for the for, you can iterate over something. If you have a database cursor, you could iterate asynchronously over the results of that database query and then work with it in a for loop, just like a normal for loop. So kind of like makes it into this magic iterator thing that's asynchronous. So that's cool. I don't know, maybe I'm just having a bad week and I'm sort of like negative on it. Twisted, for example, doesn't have anything like this, so this is built into the language, so this is nice. And Twisted, I think other frameworks can leverage this type of enhancement to the syntax, but it does take a lot to sort of like get your mind around. You can also define your own like awaitable objects, kind of advanced, but if like we were looking in before, the for loop or the lock, like you could define an awaitable thing that would be asynchronous, and so when you it's kind of like a callable object, but not exactly. Pretty advanced, but you can do. There's a lot of new double under methods in async that asyncio has kind of come up with. So if you want to really understand this, this is the stuff you should read. There's a whole lot of content here. This PEP 3156, that's kind of the main one. It's way overloaded with stuff. It's got the event loop definition stuff. It's got the transports and protocol stuff. It's got the scheduler stuff. It's really kind of a lot. But that's a good one to read. Yeah, some of this other stuff. So the yield from and the original kind of like coroutines have actually been in Python since 2.5, but they were never kind of like done asynchronously like this. So that 342 PEP is kind of the original. How do you do coroutines? They're kind of cool. They're like generators that you can send stuff to. So that's kind of a fun read. It's only tangentially relevant to async. All right, so what about frameworks? So Twisted is obviously kind of the biggest one. It's been around for a long time. It's got all kinds of sort of patterns or cruft built up, obviously. Like if it's any code base that's been around that long has some warts, but it's pretty good in general. All of my stuff, I work on vehicles, autonomous vehicles that communicate asynchronously with Rabbit or AMQP messaging. All of it's in Twisted. I've been living in Twisted for like the last year and a half. It's production ready. It's very, very solid. Well tested. It's also more than just an event loop and some like scheduler and some client server stuff. It's a lot of utilities, locks, built-in lock support, other types of things. This is Amber Brown's the release manager for the project. Async.io is an apple, Twisted is a fruit salad. There's just a lot more to it. There were, when Async.io first came out, a lot of people were like, oh, well, Twisted's dead, right? Like, why do we need it anymore? Because we have it in the standard library. I think same thing with Tornado, like these other frameworks, they add value. I like the idea of kind of like plugging into a central kind of standard library thing and then building on top of it. And that's kind of the direction they're headed. I think it's slow. It's probably slower for Twisted because it's just been around longer and it's a bigger framework. Tornado is, I think, a lot further along. I don't know as much about Tornado. We'll talk about it in a second. But some things I said earlier, I like Twisted stuff a little better than the asyncs. I think that future task stuff is a little weird. Twisted has this deferred object concept, which is sort of the same thing, but I just feel like it's implemented better. That's probably, a toss-up between the two, really. It's probably more about what you're used to, but the idea is basically the same. You can use deferreds to schedule callbacks again, schedule airbacks against when things fail. That's kind of an opinion. Twisted does have this async.io reactor. You can drop it in, replace it. The coroutine support in Twisted, you can't, as far as I can figure out, Twisted coroutines, like you can't do the native async stuff yet with it, partly because of this deferred versus futures thing. I'm on a code base that's still in Python 2 with Twisted, so I'm not totally like up to speed with like the actual integration. But this seems to be a sort of problem with integration of Twisted and interoperability with the async stuff. Tornado, basically a really fast, highly concurrent web server. It has automatic support for async.io for quite a while now, like maybe a couple years. So you're basically using it if you start using Tornado, from my understanding. I haven't done a lot with Tornado. Django is also doing some experiments with this. So there's Django Channels. It provides a bunch of different kind of the protocol stuff. WebSocket support is probably the biggest thing. If you look at the web space like Node.js, WebSockets are kind of a big feature that Node.js can offer, that there's really nothing that's great on the Python side. That's what they're trying to do with Django Channels. So basically you get this async layer with Django that you can use for things that you need to do asynchronously, like WebSockets. And then you can also just like route around it. It has this like whole routing machinery for should this be an async request or should this be a sync request or whatever. It's a little, I think it's a little awkward, but it's a good start. This is also referencing Django Channels 2.0. Django Channels 1.0 is totally different. 2.0 was rewritten to use async IO. There's a great talk from PyCon this year that gets into some of this and where it's at. To me, it feels like it's a little bit stuck at the moment, but it's like not clear how to move forward with things, partly because these two paradigms are hard to mix together, like we talked about earlier. And then there's the sort of async IO native ecosystem that's come around in the last few years. We looked at AIO HTTP as the kind of the requests library equivalent. Postgres database support for asynchronous interaction with databases is definitely an area that you're probably going to want if you're doing this and you're using web apps or you're building web apps. So these are kind of like the highlights of things. There's a whole bunch. Yeah, it feels like it's still pretty early, like the ecosystem is not really fleshed out yet, but it's getting there. So after I complained about this for like 20 minutes, like why would you actually want to use it for anything? Well, there's this C10K problem, so it's shortcut for concurrently supporting 10,000 connections or 10,000 sockets. This is what Tornado is really designed to solve, basically, and this is why Node.js has had kind of, I think, some of the success that it's had. Asynchronous programming is perfect for this because you have all kinds of like dead time when you're waiting on clients or waiting on servers to talk back and forth. So having this event loop and scheduling these callbacks, it's perfect for that because there's all this sort of air in the system. So Django Channels trying to do that. I think there's a couple of other like newer frameworks that Python world is coming up with. I'm sort of an old school fan of Django, so I would love to see them be able to make that work. So far, I feel like it's kind of not there. If I was going to write something WebSockets, for example, I'd probably do it in Node, but that's probably not something I should say at a Python meetup. So games, you might have games. I originally learned how to do asynchronous like select polling, writing text-based adventure games like 20 years ago. That's kind of an obvious use case, right? You have 100 telnet connections. You're trying to iterate through them and send output back and get input from them. And there's a lot of dead time, like the user's just like reading the screen or whatever. But obviously, most people aren't making text-based adventure games anymore. Real games could be implemented this way. There's a lot of similar patterns in terms of the network I/O. And then this is what I do. So IoT devices, sensors, where you have lots of data being gathered by lots of different sensors, or in my case, fleets of vehicles driving around. This is actually pretty interesting for that because it's the same idea. You're having a lot of concurrent connections. You're waiting. There's like a lot of dead space, dead air, where you're just like not doing anything because you're waiting for communication back and forth. Now, dead air, it might be like microseconds, but it's still like nothing's happening. So event loops are really good for kind of like working in that space. And I think this is probably a growth area that like right now, Node and all the async stuff that you see in the world is mostly web-based and web-focused and these like, multiple clients connecting. But as we get more into this type of IoT robotics stuff, sensors and other things that are gathering a lot of data and a lot of, like a large distributed system, sending stuff back to a central server. I think that this is probably a pattern that could be more broadly used for stuff like that. And I'm happy to talk through questions or anything on that. That's actually the end, but I will take questions or we have a conversation or whatever. Go ahead.
Yeah, so I've never done any asynchronous programming myself. But is it the case that anything that you can do asynchronously, you could do synchronously, or in a standard. So is it just the doing things asynchronously is cleaner and is easier to write the code and to think about in that context?
Yeah, so you could do anything you can do in one, you can probably do in the other. The difference would be this idea of like, it's really the I/O piece. So network I/O, where you're waiting on something to come back, and you like literally can't do anything until the server gets back to you, right? So if you're doing synchronous code, you just have to wait. Like you can't do anything else in your program until the server gets back to you. You probably wouldn't want to use asynchronous programming for anything that didn't have a pattern like that, where you're doing a lot of network I/O, because it's just more complicated. Like it's not necessary to add that layer of complexity.
Okay.
Does that like answer the question?
Yeah, I think so.
But you could do anything. Like you could do, like you can run NumPy or whatever computational stuff asynchronously. It's just the processor, like it's still single threaded, right? So the processor is still going to be tied up when you're doing computations, which is going to block. So if you're doing things like that that are computationally heavy, it doesn't make sense because you're essentially doing synchronous programming anyways, but you're kind of like making your program more complex with all this callback and event stuff.
To address part of it, if you wanted to handle a lot of the network pausing, the other approach would be to use threads. But the problem is that if you're using a thread per request, you need to have very lightweight threads, or once you get up to 100,000 concurrent requests, you're using a lot of RAM. So that would be the difference between the Python and the Go models. With the coroutines, which are very tiny fibers or threads, you can have a few 100,000 of those without an issue. Whereas in other languages like Python, where the threads are much heavier, you don't want to do that, and so you're looking at things like async I/O as an alternative. Yeah. That helps.
I would say like this asynchronous stuff, it's a little, if you're trying to prove out a concept, you should probably just use threads initially until you've proven it, and then maybe convert to this, because you can kind of do the same things. The only reason you would use this over threads is exactly that reason, because your overhead is a little bit higher.
Never having done asynchronous programming, are the things like the locks and the events on waiting for things, that's do a lot of protection against things like race conditions and such.
Yeah.
I just wonder, like, is there a lot of protection against reading something before something's written?
Yeah, so a good example with the context manager, the asynchronous context manager, is doing transactions in a database. So if you want to lock the database before you do writes to it or something, doing that with that async context manager would be kind of like a lock, where you're just sort of like, okay, I need to start a transaction, wait for the database to tell me that I can do that, get my transaction back, do my stuff, and then release the transaction automatically. So the async with statement, you could do something like that. But that's exactly why you'd want to do it, is to avoid those kinds of things. If you're integrating with other external systems, like I do a lot of integration with like PLC systems or little like electronics things. Some of those are like you write them out through like bitwise operations, like you're just like writing bits out straight. So you'd want to like lock access to stuff like that while you're doing your write, unlock it when you're done, and then something else that might be trying to do it could do it. So yes, exactly those use cases.
There's something like JavaScript's, you said futures or like promises. There's something like promise.all where you kick off a whole bunch of stuff and you say, I want to wait till all.
Yes. Yeah, so you can create tasks with like this function. There's several of them, but like I think all is actually one of them, where you can pass in a whole bunch of futures or coroutines, and it'll just wait until it'll turn those all into a task or different things like that.
Is that kind of what the async for is doing, or I guess that's more one at a time?
Yeah, that's more iteration. So you could be iterating through rows, like, batching up rows in a database and like iterating through, and then have an asynchronous retrieval of the next batch and stuff like that.
Oh, I see.
Yeah,
And so that if there was something like under the hood where you're like firing off multiple services, you still have to do that.
Yeah, you could. I mean, you could have two coroutines running that are doing different for loops over different like databases or sources of information. It's kind of funky.
That's a lot of
And it's a little confusing where like some of this stuff is just asynchronous programming in general, and then it's sort of embedded in async IO, like things like that could be useful, like a futures or something,
Yeah.
And but then the keywords async in a way are definitely useful, but it sounds like since you're still using a single thread, you don't necessarily want to use it for like some big calculation.
Right.
So like you said, this wasn't a twisted killer because it had those think frameworks like that are sort of value added. Imagine it also doesn't kill like task managers like Celery.
Oh, totally. Right.
Okay.
Yeah. I mean, you can start doing really crazy things like spinning up threads and running event loops and threads and then having stuff talk back and forth. And there's a lot of different kind of architectural patterns, but it doesn't like multi-processing is kind of what Celery is good at. So you have multiple task workers running on a distributed cluster or something, and they're pulling things off a queue or whatever. That's like a different kind of concurrency than this. This would be where you need things to be like a system where you need to have kind of a central state and kind of central management of execution and stuff, but you have a lot of stuff where you're just waiting all the time. And so that's a really good use case. So like vehicles, robots driving around a factory, there's a big gap in time where they're not telling you anything because they're just moving, and then they're like, oh, hey, I'm there, and then you get a response, you get a message, and so you want to coordinate those with other things. A system like that versus something where it would be distributed and the workers don't know anything about any of the other workers. They're just kind of like dumb and doing tasks.
I do have a question, but I guess it's the difference between like a chat app, which is like a really good fit for something async, and rendering PDFs, which would be great for Celery, right? Where you're just trying to do some work out of core process, but like that PDF thing is happening. In terms of like these fancy packages, have you played with any of the other alternatives, Curio or Trio, or there's like a couple of folks who have been like, this async IO thing is completely insane. We're going to write our own from scratch, and I don't know.
I watched a couple talks of Curio stuff at PyCon. I haven't really played with it. It's interesting. What's kind of interesting, the Twisted people talk about how before Node.js came out, they had to like argue for this. Like no one wanted this in Python. There's like, why would you ever do async? Like it's just silly. And then Node.js came out, and they don't have those conversations anymore. And I think it's interesting because the pattern in the Python standard library has been you land some stuff like URL lib or something, and it's kind of terrible, and then somebody builds requests or some other thing. So maybe there's a similar pattern happening where, not that like URL lib is terrible, it's just like trying to do so much and satisfy so many people because it's a standard library module. I think it's just kind of like overloaded. I think a pattern like that could be happening here. So Curio and these other third-party projects, Twisted, I hope continues to be kind of thriving.
I think some of the history was like that this got in because they wanted a core, like that future task primitive that could be used to allow like interop between, say, Twisted Tornado, and people want to cook up other things, and so I think there was motivation to can we get some object in the standard library that everybody all these different async libraries can use and agree on. And I feel like the problem was that they couldn't just do that. They had to provide this whole framework. And really, I mean, there's parts in there that came in 3.4, and by like 3.6, they're like, this is deprecated, don't use it. And it's really felt like a lot more of the maturation of async IO has happened once it was in the standard library compared to other things that have gone in that have a lot of that maturation has happened like outside the standard library. It's kind of a public thing, and then people are like, this is awesome. Let's bring, ultimate stable. Let's bring it in. And this sort of feels like we need something, and people are clamoring, and we better do something.
I think there was a lot of that where I was like, we're losing to Node, so we need to do something.
Yeah, we were losing to Ruby and Rails 15 years ago. It was fine. It's interesting. I know some of the Twisted guys, and I wanted to ask them, because if you look at Twisted code with the callback style, it just looks inside out, right? Like you write what happens after as your callback, and then you attach it to something, and so just everything looks upside down. And I asked him about it, and I was like, what does normal Python code look like to you? You guys spending writing callback style. And he said it just looks wrong. He's like, it's like you just look and you see all these spots where it could block, or there could be, you're making a call to URL lib, and there could be an exception, and it's just not handled. And he said, he looks at the clip. He said, I look at normal Python code, it just looks wrong. Everywhere, because there's all these things we just don't usually deal with, and and then you try to deal with them all, and you get twisted.
Yeah,
that was pretty wrong too.
The exception thing is actually a good thing to mention. So like Twisted has the same problem. Since all this stuff is kind of running in these coroutines, there's a tendency for like exceptions to get sort of swallowed up. So the framework or the infrastructure has to kind of capture that and bubble it back to you somehow through like an airbag, or there's different ways. That can be really annoying because you need that to debug.
And that was gonna be my next question. Is just when I've done work more in Twisted, is like debugging this stuff. And I don't know if your experience with Twisted or asyncio is any different, but debugging this stuff is kind of impossible because there's no call stack, right? Like,
yeah,
you make a function. It's not like you make a function call and you're going to return from that function call the place you were. Like, you do some network I/O and some callback is going to get called in the future, and then you exit your function. Like, there's no way of like visualizing a chain of callbacks the way there is, a chain of function calls that you're down in the stack. And so you get tracebacks, and you should know what's going on.
So logging is definitely your friend. That's kind of the best thing that seems like if you look at Twisted, like the logging module is sort of a big part of it. Being able to do structured logging is also really nice, so you don't have to like parse text strings and stuff like that. But yeah, it's not easy to debug. Good test coverage and things like that make it better, but yeah, it's rough. And then you get these weird situations of like, oh, something's blocking and I didn't realize it, and then I drop some messages or something, and like, how do you find that? So that's why you would not want to do things asynchronously unless you kind of had to, right? So it's like a lot harder to debug because things just kind of spin off by the event loop, and you maybe never hear from them again.
So it's really for just like industrial strength data I/O.
Yeah, definitely like networking I/O is one of the best use cases. There's other things you can do. Like you'll see some stuff in the async I/O module will let you do communication between processes, like inter-process communication. So you can do stuff like that, but generally like network I/O is sort of the big thing.
A little story up front, like in the mid-2000s, when XMPP with Jabber was like the instant messaging protocol of choice, there were a couple of competing servers, and there was one written in Twisted that beat the pants off one.
Yep.
Yeah. And they're like, how can this possibly, this is like by factor like 10 or 50. Like, how can scripting language possibly do this faster than concurrency? And it's like, well, all you're doing is waiting on sockets all day.
Yep. Yeah, there's no real magic to it. This has been around since like the 70s. It's just before you had the internet, there wasn't tons of use cases. So, other questions? Cool. Thanks for coming. You can hang out afterwards. This is great.